So we end up with this network. I wanted to spend this next video kind of discussing um, DOPS specifically and explaining the concepts behind DOPS and how DOPS works. Um, and so because this will ultimately benefit you when doing crowd sims, because crowds are entirely in the DOP context, or primarily anyways. So in order to do this, I'm going to use this very simple example. And it's when I like to use this example whenever I'm introducing students to DOPS, because it's a very simple example, and it kind of can give you an appreciation for how DOPS is different from SOPS, but it also is showing you kind of the DOPS equivalent of SOPS. And this will hopefully become clear as I go through this example. This file, I'll include it so you'll have access to it. And the file is really well annotated, so if you need further explanation, you can also take a look at these notes and see what it's doing. All right, so here I have a sphere, and just a regular old polygon sphere. And then I've created a VOP network, and inside the VOP network, I've added some noise. Great. So this is being done in the SOPS context, or surface operator context. So, this is fairly straightforward. I'm just computing some noise, adding it to the position, and putting it back out to the position. Great. So one of the ways that, to think about how SOPS works conceptually, and it's useful to have this picture in your head, particularly it'll help when contrasting with DOPS and how it works, is that SOPS, each node has a copy of the geometry, and then it's performing some sort of instruction. So in the case of the sphere, it's creating the geometry and just putting it in place. That's all it's doing. In the case of this VOP network, what's happening is it says, okay, I'm going to copy the sphere geometry, make like a discrete copy of that, and then I'm going to perform some sort of operation on that incoming sphere geometry, namely noise it up. So I find it's useful to think of this in terms of nouns and verbs. So the noun is the geometry that we're going to perform some action on, and the verb is the action that we're going to perform on it. So this geometry, one of the things about SOPS that's great is, it makes a copy of the geometry. And what's nice about this is once a node evaluates, it doesn't need to reevaluate as long as you don't change anything, either in the node or upstream. So I can come to this sphere and look at it, and then I can come back down to, this attribute VOP, and it doesn't reevaluate. Once it's cooked, and it makes a copy of that geometry and puts it in memory. So the good part of this is once it's cooked, you don't need to recook, you're saving time. The bad part is that it's creating a second copy of the geometry in memory. In this case, that doesn't really matter. We're using a really small data set. We're not really concerned about RAM usage. But if you're using, a large data set, it becomes a problem because you're making copies of that geometry and it's being stuffed in memory, and you'll run out of RAM. As a quick aside, for those of you who don't know, there's a way to mitigate this with compile blocks. We have a masterclass on that. You can go check that out, but that's a separate topic. But in general, just vanilla SOPS, this is how it works. Okay, so over here, I've made the equivalent of this SOP network, or the DOPS equivalent. And the first thing you'll notice is it doesn't really evaluate on the first frame. First, I'll just show you what it does, and then we'll kind of talk about how it does what it does, why it does what it does, and the kind of structure and philosophy of DOPS. So we have a sphere not doing anything, and it's on the first frame. This is because by default, DOPS doesn't evaluate on the first time step. There's ways to change that, and I'll show that later, but by default, it doesn't. So if we go forward one frame, it evaluates. So, and if we look, these two guys are exactly the same. And the reason why, and I'm briefly going to dive into this node, is because I've basically made a geometry VOP inside of DOPS. And I'll get into more detail about what all of these nodes do, but for the time being, just pay attention to this geometry VOP. I've created this geometry VOP, and inside of it, it has the exact same node network. As a matter of fact, I believe I just copied it from the SOP context into the DOP context. So yeah, so they should look exactly the same. One of the differences, though, is that DOPS is a simulation, so it's going to keep adding noise every time step, while the VOP network does not. So it's evaluated, and it evaluates discretely on each frame. In this case, it's not evaluating each frame because the input isn't animated and there are no animated parameters on the VOP node. So once it's cooked, it's cooked. It doesn't need to reevaluate until the graph is dirtied, which means the input's changed or one of the parameters on the nodes changed. In the case of DOPS, it's a simulation. So a simulation needs to have information about what happened on the previous time step to modify what it's going to do on the current time step, right? So this is the major difference between DOPS and SOPS, right? SOPS is meant to kind of evaluate discretely on each time step without regard for what happened on the previous frame, whereas DOPS is very much interested in what happened on the previous frame. Okay, so with that explanation, let's dive inside the DOP network and kind of take a look at what's going on. So here we have this very simple network, and you can see that already it has more nodes. So let's talk about these nodes and what they're doing. The first node is called the empty object node. And I'm just going to go back to the first frame to reevaluate the graph. And we can display that and look at it, and we don't see anything in the viewport. This is in essence because it's an empty object, it's an empty container. It has nothing in it. If we come up to this geometry spreadsheet and we take a look at it, what we see here is we have our geometry spreadsheet. It looks a little different than what we're used to in SOPS, but that's okay. So we have this empty geometry object, and it's got some pieces of data, kind of default data, attached to it. But this is basically an empty container. And you can see that it's being named object name, and this is the default, which it gets here. You don't see anything in the viewport because it's just an empty container. Great. The next node is this SOP geometry. And so this is importing geometry from outside the network. So if we click on this arrow and follow it, it's going to fetch the data from the sphere and bring it into this SOP geometry, this node, right? Or into what it's doing is putting this geometry into the empty container that we created here. So let's take a look at that, the geometry spreadsheet now. Okay, so we have our empty container that we made, and we've now put geometry into it, the sphere. And if we select the geometry, we see we have what looks like a very recognizable layout of information, right? It's exactly the same as a geometry spreadsheet that you see in SOPS. So this is basically, you can make various different types of data into a container. In this case, we've made some geometry, and we've put we've basically taken the information from SOPS and put it into this empty container. Okay, so what comes next? Groovy. Next in the chain is we have this multi-solver. So the multi-solver is basically a way of, you can think of it as a way of joining, well, it's a way of taking this geometry that we have and processing it in some way. So this is a geometry that we want to process, and then this is the process we want to run on that geometry. In this case, it's add noise. So we display this guy, and then we can kind of move forward and see that it's actually performing an operation. So with the SOPS example, I talked about this idea of you have a noun, which is a geometry, and then you have a verb, which is the action you want to perform on that geometry. The equivalent here is, this is an empty container. It's putting data in it. This is our noun, right? And then this is our verb. And then this is saying, perform this action on this noun, run this verb on this noun. And then at the end, we have an output, which is just telling the DOP network where to look for output, or what the end of the chain is. Okay, so the way this graph evaluates is it evaluates from top to bottom and left to right. So it'll start off by going, okay, make an empty container. In that empty container, put this SOP geometry. This is a set of instructions. In this case, add some noise. And I want you to perform this action on this noun. And the way I like to think of a DOP graph evaluating is it's collecting data and then these kind of verbs or actions, and it's putting it all together. And once all that information is, collected, so once you have the data you want to act on, or your noun or the geometry, and you have the instructions that you want to perform on that geometry, those things are collected. So it's like the data and the instructions are kind of being assembled. And once they've all been assembled, then it gets evaluated. So I like to think of this as I'm taking data and collecting a bunch of different instructions and kind of putting that all together in a specific way. And then once I have the data and the instructions, then I will evaluate. And that's the kind of paradigm that I keep in my mind in terms of how DOPS works. And it's a little bit different from how SOPS works, right? But if you can kind of keep that in your mind, you'll understand DOPS a lot better. Great. And yeah, and then we can move forward and we see that it evaluates. The last kind of thing that I wanted to discuss here was this phenomena of non-evaluating on the first frame. So this can be changed by turning on this toggle here, solve on creation frame, and then it solves immediately on the first time step. The reason why it's off by default is because take a scenario where you have a large sim where, say, you have hundreds of thousands of agents, or you have a very large pyro sim. Each time step will take a significant amount of time to evaluate. 30 seconds, 10 seconds, a minute, depending on the scale. One of the things about working with the sim and finding the right settings and getting everything to work is one of the actions that you do quite often is, you scroll forward, you look at the sim, you change some parameters, and then, the graph become, you change some parameters, like I'll change the frequency here to 10, say, and then you'll notice that, okay, I now have to reevaluate. This simulation is no longer valid, so I have to go back to the first frame. So you control up arrow to go to the first frame, and it reevaluates. the thing is if your simulation is really large and each time step, takes, 10 seconds, 30 seconds to evaluate, a minute, whatever, every time you go back to the first frame, you're going to have to wait that 10 seconds, that 30 seconds, or that minute for it to evaluate. And that's, in terms of working, that can be, slow you down. So we have this option to turn off solve on creation frame to avoid that problem. And that's why it's there. And that's why it behaves this way by default. Okay, in the last video, we talked a little bit about the difference between SOPS and DOPS kind of conceptually, and hopefully that kind of gives you a little bit of intuition in terms of the difference between the two, and it'll give you a bit of an appreciation for working in DOPS and some things you kind of need to consider. So this is the graph that you get when you click on the simulate button. There's and hit the terrain button as well. I wanted to just kind of briefly discuss what these branches kind of represent, so you know what it is we're dealing with, and it's just not a mystery. We'll start off on the left-hand side here. We have our terrain object, which is basically just importing the terrain from the SOP context. And that's going into a static solver. And what that basically says is this is going to be like a passive collision object. It's not going to be something that's simulated. And this is going to be used by the bullet solver over here, which is going to be in charge of taking care of our ragdoll physics. So that's what that is. Then if we come over here and we take a look at this branch, we have our crowd object. You can think of the crowd object as like the equivalent of this empty object that we used in the other example, or this basic SOPS versus DOPS example. And so, yeah, and as a matter of fact, if we just, you don't have to do this, you can just watch. If you go into allow editing of contents and crack open the digital asset and look at it, you see we in fact have an empty object, and then we're using SOP geometry to kind of do various things, namely, add different types of geometry, which is the same thing that's being done over here, right? SOP geometry. So there's like more is being done, but there's an equivalence there. So I'm just going to match current definition to kind of lock up that asset. All right. So this is like our empty crowd object. And then we have some nodes over here for setting up constraints. And these are basically being used along with this constraint network node to set up constraints for our agents, so that we can do the ragdoll physics with them later. Then over here we have our crowd source, which is going to be importing our crowds. If we display it, we're not going to see anything. This is because in order to source the crowds and import them, it needs a container to put them in. And at the moment, there's no container for it to put it in. If we can come down here to the crowd solver and take a look and it still doesn't evaluate, well, that's because it doesn't have this container yet. As soon as we come down to the multi-solver, then it can evaluate properly and get that container where it can actually source the crowd agents into. So the sourcing of the crowd agents is just say, hey, go look at this crowd source node, bring in the geometry into the DOPS sim so that we can, and put it into this empty object so that we can do something with it. We have the crowd solver itself. This is what actually does the simulation. And over here we have our state nodes, which are our walk state, our run state, and ragdoll state. Over here we have a merge that currently has nothing in it. And what this is for managing transitions. We have what we'll have here is a trigger DOP and a transition DOP. And the trigger DOP is responsible for saying some event has occurred and I want to change from one state to another, like walk to run. Go ahead and do that. And then following that, you have a transition node, and that basically says, switch from how am I going to switch from this walk to run state? We're going to get into that in another video. So don't worry, that's coming up. I just kind of wanted to give you a little bit of a preview. And then over here we have the bullet solver, which is going to be used for doing ragdolls. Obviously, if you're doing a crowd sim and you don't have any ragdolls in your crowd sim, you don't need this bullet solver. You can delete it. You can blow it away. And then down here you have a node for gravity. This, again, is going to be used for a bullet solver, right? Once ragdoll physics are enabled, you want your ragdoll to kind of fall down. So that's why this is here. If you're not simulating, then you don't need it. Yeah, just good stuff to know. All right. The other thing I wanted to do is, actually, let's talk briefly about, how this evaluates, right? So it's top down, left to right. So, these instructions kind of get put together here and they collect here in this merge. Likewise, these branches, we're going to go top down, left to right. So this branch and these branches get evaluated. They kind of collect down here. Then the next branch kind of gets evaluated, comes down here, and the bullet solver comes down here. Those get collected here. Gravity gets added. And remember what I said earlier in the previous videos, you think of these as a set of instructions and data that are kind of getting assembled together. And once they're all assembled, then the evaluation happens. It's not like SOPS, where as soon as you display a node, there's an evaluation. In order for the sim collectively to kind of work, all of the instructions and all of the data need to be put together and then evaluated. Okay, groovy. Let's take a look at the geometry spreadsheet here and see what we have. Okay, so we have our crowd object, right, which you can think of as the container, the equivalent of, this empty object over here. And then it's got a bunch of different data inside it. And you notice that a lot of you have your geometry, which is basically your crowd agents, right? Each point is a separate agent. And those agents all have IDs, attributes on them that, provide you with different information and is used by the simulation to compute different things. Things like velocity, the current state. You have an ID attribute, which is, a unique identifier for each of the agents. Clip times, state duration. I believe that's down here somewhere. Yeah, state duration, steer force. So there's lots of different parameters here, lots of different attributes here that are going to be used by the sim, but also you as a user can query any of this information and manipulate it. And this is a lot of how you get control over your sim. You'll notice that there's this like little box icon beside the geometry. That's because it's geometry, right? And you'll notice that there's other like pieces of data in here. So you have things like, your constraint geometry, which is for going to be used by our ragdoll physics. This is just being, represented by geometry. And it's got its kind of own section that you can query and modify. But it's helpful if you, can look at this and say, okay, we have this empty container, and then there's a bunch of different pieces of geometry or, geometry containers within this container. And those, that geometry has attributes and different properties that we can manipulate. You'll notice that some of these are empty, like clip graph and clip graph paths and clip properties, are empty. but we're going to be adding information to this later. And yeah, so we'll revisit this as we progress and get into transitions and triggers. You'll notice that states has its own kind of geometry section, and it's represented by these points with data on it. Walk, run, ragdoll. So yeah. Okay, so we come back to this viewer, and there we go. All right, so that's it for this section. I just wanted to kind of discuss the network and its construction and the general kind of broad meanings of it. In the next video, we're going to talk about adjusting this walk cycle. So it has this bad loop in it, or it loops kind of badly. So we're going to talk about getting this kind of pop. You can see there's a pop there. We're going to talk about ways of getting rid of that. In this video, we're going to talk about making adjustments to your clip. In particular, if we take a look at this agent right here. As he walks forward and he reaches the end of his clip, there's a pop, right? And this is because the end of the animation clip and the beginning of it don't match. And so, a number of ways you could fix this. You could try and actually, fix the animation. But there's a convenient way to take care of this without having to do that. So I'm going to go to the object level, and I'm going to go to the setup area here. And I'll just move the foot plant channels over to the other side. And I'm going to drop down here a agent clip properties. And I'm going to stream this off of the agent prep. So just go. Okay, and let's see. All right, next thing we need to do is we need to specify the clip we want to work on. So we need to have a clip, and I'm going to choose walk. Great. And pull back a little bit. There we go. So here's a clip, and if we go forward, you can see there's a bump there, which is what we want to try and avoid. So there's this option down here for blend while looping. We can kind of go forward. And now that bump is reduced quite a bit. Still a little bit of a jiggle there. So, but this animation is actually, kind of bad. So, particularly where it loops. So, we can just, we can mitigate that also by the walk cycle here. If we take a look at it, that last frame is, it gets pretty egregious. So let's just maybe instead of 26 frames, we can do 25. Let's see what we've got. Okay, so there's still a bump there, but I think this will hopefully be a little bit nicer. Yeah, and it looks much nicer. So a kind of combination of clipping off some of that bad animation at the end and also enabling this looping. Let's turn it off, just see how it looks. So you still get that pop, right? The arms are in different positions. So we turn on blend while looping, and it looks much better. This is set to 3 frames before and 3 frames after. The the loop point. You can, of course, adjust this to whatever you see fit. I'm going to type in tab here and create a null. Nulls are just really great placeholders to kind of, if you're going to have another network referring to another node, it's nice to have these. I'll call this properties. It's also good to keep in capital letters because it's easier to search from the menu. And yeah, let's see. Then what I'm going to do is go over here back to my crowd sim. And on the crowd object, there should be an option for clip properties. So we can go over there and come click on this, and then we can browse for that properties node. And that's in the mocap biped 3 setup. Click on properties and hit accept. And let's back it up and zoom into our sim and take a look at what we have. Great. So it looks like that, really bad bump has been kind of removed from the clip. So we're in good shape. All right. One of the things you'll notice here, if we come over here to clip properties, and you'll see that we now have information in here. If we remove this, back up to the beginning of the sim, it's empty, right? So when you add your clip properties, sorry, I'll just undo this. It's nice to have an appreciation for, what is occurring, right? So you're grabbing some geometry from SOPS and you're putting it into this crowd object, and specifically in this kind of area called clip properties. So this information now exists, and this is how the sim in turn accesses this information. And I'm letting you know this because it kind of demystifies DOPS and it demystifies crowd sims a little bit. And you just also will have a little bit more of an appreciation of what is going on inside of DOPS and where this information is being held. Okay, so that's clip properties and making adjustments to clip properties. That's the end of this video, and I will see you in the next one.